Hi, welcome person who are taking various Monday AP, what's today's AP?
Bio and physics.
Bio and physics.
And music theory.
And music theory. Good. Hey Randall. Let's begin. So last class, which was Friday, we proved, class ended with, Dylan, you got mad at me for doing an inelegant proof. I talked about you in ninth period. In ninth period, I just did the chill proof. Like, yeah, they liked it better. Randall knows better, right? Yeah, it just was. You were right. So what we did on Friday, recall, so just like recall, that we were talking about Polyhedra, and in particular we were talking about the Platonic Solids. We proved that there were only 5. How did we do this? We first had a formula that said that the number of vertices plus the number of faces minus the number of edges is 2. And this works for any planar, simple, connected graph, of which all polyhedral graphs have those properties when projected, as long as you count the outside region as a face. And then we broke this up into, like we said, like let V be the number of vertices, kind of like F is the number of faces, and let's just say E because, I'm going to use epsilon because I feel like it is the number of edges. And then we said let B be the number of edges per face. That's really what this is. What this essentially is, where we call it the number of bounding, the degree of the region, or the number of edges bounding each face. And then we also had N, which we said the degree of each vertex. But phrased as a polyhedron, phrased as a statement about polyhedra, it's saying the number of edges meeting at each vertex is equivalent to saying the number of faces meeting at each vertex, yeah?
Yes.
So it's really the number of faces per vertex. All right, and now we see we have kind of like some sort of counting. And then what we did was we did a whole bunch of, like relationships between these properties, and we reduced this to, if I recall correctly, 1 over B plus 1 over N is 1 over epsilon plus a half. I believe this was how we did it. Yeah? Okay, and then we mentioned the 5 Platonic solids by saying, okay, B and N can't be very big, so it's like plug in numbers and stuff. All right, well, yeah, good. And then, did we talk about Loffley notation yet in this class?
Yes.
Yeah, we mentioned that at the end of class. Good. So the Loffley notation for describing regular polytopes is, I think it was in 9th period that I did it more thoroughly.
You did it more here.
I did it more in this class. Okay, great. Yeah, so we have the regular polytopes in 2 dimensions, which are just the regular polygons. So that's like that's like an equilateral triangle. That's a square. That's a regular pentagon. Etc. And then we have it's like a recursive notation. So this is in 2D. But in 3D we have, like the tetrahedron, for example, is 3-3. Can you carefully get me the tetrahedron? You can get up on a chair. The tetrahedron is 3-3 because it's 3 triangles meeting at each vertex, and the cube is 4-3 because it's squares 3 meeting at each vertex. And what would the Loffley notation be for the octahedron?
3-4.
3-4. Yeah. That's because it's triangles 4 meeting at each vertex. So this is like important. I think we should all know the Loffley notation. So this is like actually expecting you to know this. All right. What's the Loffley notation for the dodecahedron? 3 seconds of wait time. All right. It is 5-3. Yeah, because we have pentagons 3 meeting at each vertex, and finally the icosahedron. 3-5. Yep. triangles 3 meaning edges 6. All right. Well, phrased in the so this is 2D, this is 3D. Phrased in the vocab to the left. What am I really telling you? When I'm telling you the cube is 4, 3, what am I really giving you?
Description of each vertex.
Yeah, explaining like what is 4. 4 is
The type of polygon meeting.
B, says Rafi. Thank you. And what is 3? N. Yeah. And so actually that's kind of what the Loffley notation gives you in terms of our old terminology. It's giving you the B and the N. So notice that this notation describes sort of what the shape is like locally. And from this, we can derive all the various properties that you need. So take the octahedron, for example. I was pretty sure I should like credit the people who like just taught me how to do this 5 minutes ago as the bell was ringing. So thank you, those people. What's up?
Yeah, certain person from your alumni who got
Oh, who's that?
these.
Oh yeah, don't interrupt my video with math counts anecdotes. Alright, just like you can just like watch that later. It's very exciting, I suppose. But alright. Octahedron. Alright. So we all know everything there is to know about the octahedron. So if you grab the octahedron off the shelf, but and just like, you know, hold it in front of the camera and give it a little happy spin, smile, etc. So the octahedron, we think of it because we're like familiar with it as like this shape composed of like 8, you know, equilateral triangular faces, like etc. But that like maybe is like too much information, right? I claim that we can uniquely, okay, that's good. We can uniquely characterize it by its like local behavior, and this is the power of having proven all these various theorems and relationships. All I really need to tell you for you to know every single thing there is to know about the octahedron is, Tyler, what do I need to tell you? Just this. Boom, 3, 4. Just that it is a regular polyhedron made up of triangles with 4 meeting at each vertex. Okay, well let's see how that just completely tells you everything you need to know. Well, so start. What do I know? I know B is 3. That means it's composed of triangles. I know N is 4. There are 4 triangles meeting at each vertex. So let's compute the rest of the properties. Well, we can just plug them into this equation. What do we get?
7/12 equals 1/2 plus 1 over E.
7/12. We can do like math in our head and stuff, right? 7/12 equals 1 over epsilon plus a half. Therefore epsilon is 12. Ooh, it's kind of incredible that we just get the number of edges. Not incredible, but it's cool. That we got the number of edges immediately from the from this relationship, and then we can also get the number of vertices and the number of faces by like kind of like reverse handshaking from Friday, right? What do I mean by that? I'm not totally sure. If I now know the number of edges, but I also know the number of edges per face. No, that's backwards. If I know the number of edges per face, which is, so B, the number of edges per face, is just times the number of faces, which I currently don't know, is just going to give me the number of edges, just like that.
Times 2.
Times 2. Did I just like screw that up totally? Yeah, times 2. That's just handshake. Duh. The number of edges per face times the number of faces is twice the number of edges because it double counts all the edges. Okay, well, B is 3 and epsilon is 12, so 3F is 24, and that tells me that F is 8. Damn, boom. And then what else do I need to do? So that was a fact. This was another thing that we did. And then I guess to do the rest, we should, what's left? The number of vertices. Yeah, so, okay, if I multiply the number of vertices, V, times N, the degree of each vertex, then I've counted every edge twice as well, right? That's the original handshake. So that's twice the number of edges. Well, N I know is 4, so 4V equals 24, and therefore B is 6. So there are 6 vertices. All right, that's pretty exciting. Good. Let's everyone take a minute right now and do the same thing with what do you want to do? Let's pick the most exciting one. Dodecahedron or icosahedron? Let's do the icosahedron. Which one?
Tetrahedron.
Whoa. Okay, good. Icosahedron, go. Yep, I would like you to mathematically derive, based on these relationships, all of the properties of the icosahedron. How many edges, vertices, and faces it has. Based only upon the definition of the icosahedron, which is the local definition. It's 3-5.
No, 5.
Good.
I know how to prove it.
So the icosahedron is 3-5. B is 3. And N is 5. Degree of each vertex is 5, or equivalently the number of faces meeting at each vertex. Alright, and then, yeah, good. Continuing with this graph, so let's see. B is 3, N is 5. 8, 15, 30, minus a half of the 30th, right? Yep. So epsilon is 30. Woo! BF is 2 epsilon. So that means F is 10, yeah? No, wow. F is 20. Woo! And Vn is also 2 epsilon, so that means 5b is 60, b equals 12. So there are 12 vertices. Alright, that's like kind of awesome, right?
Yeah.
Thoughts, comments? I think it's like pictures of cool. I'm not sure if I've ever really done this in such an organized, straightforward fashion before. Come to think of it. Okay, good. Loffley notation. What do you want to do next? Do you want to talk about Archimedean solids, or do you want to go to 4D?
Archimedean
or both? Okay, good. Archimedean solids. Let's do it. I have brought. Can you go handheld because we're gonna have a big. Should we do a center table? Let's go center table.
Oh, wow.
Okay, good. These are to be touched extremely gently by people with clean hands and all that kind of stuff. So, I'm not happy with the color contrast here. No, I mean the table.
Can you disconnect this?
Please.
Is there 600 cell? Did you buy the 600 cell, Rose?
How do you? Experiencing technical difficulties.
Good. So these are my special shapes, which I keep at home. It would be nicer if this table were like a nice dark thing. But anyway, all right. So let's go. This is a whole bunch of Polyhedra, and first let's talk about our friends, the Platonic Solids. Hold on, don't. Good. Here we are. This is a particular set which, instead of having the Platonic solids have all the same size, like by radius, they did it by edge length for whatever reason. So, what's up?
You only have one of these.
Yeah, yes. Okay, hold on, getting to that in a minute. All right, sad? Okay. All right, so this is tetrahedron. Cube, octahedron, icosahedron, and dodecahedron. Cool? Great. These are the 5 regular, these are the 5 Platonic solids. Let's put those over here for a minute. All right, then if you go down one level of symmetry, we can talk about polygons what am I talking about? Polyhedra, which, stop talking. Polyhedra, which have all their faces congruent, all their faces are regular polygons. Sorry. Which is another way of saying all their edges are congruent across the board. But not necessarily the same regular polygon. So like in a dodecahedron, all of the faces are regular pentagons. But so take maybe like an extremely simple example would be a triangular prism. This is regular in the sense that all of the faces are regular. The bases of the triangular prism are equilateral triangles, and the sort of like lateral faces are squares. Cool? And by sort of like transitivity or whatever, you just get that every edge is congruent to every other edge in one of these shapes, but it's not the same kind of ones. Okay, so we have this family of prisms. So, triangular prism, the, where to go, there's got to be another cube around here somewhere.
The vertices also have to be congruent. What? Wait, what? I mean, like, they have to be shared the same by the same polygons.
Like at each vertex there's a triangle and two squares.
So I haven't even given any real definitions yet. Yes, okay, sure. Yes, a subtle point which comes up is that, okay, how exactly do we define this kind of regularity? It needs to be regular, not just that all of the faces are regular polygons, but also it's regular in the same kind of sense as before, that it should be describable like locally. This is the informal way. So I should be able to look at one particular vertex of one of these figures, and it should look the same as any other vertex. And in fact, that's true for a triangular prism, right? Every single vertex is the is where a square, and a triangle meet. Yeah. Okay. Okay. The cube is just a square prism. So we're talking about the family of prisms now. Triangular prism, square prism. Somewhere I should have a pentagonal prism. Here it is. It's exactly what you thought it was. Note that there are lots of different kinds of pentagonal prisms, but this is the only one meeting this definition because all the faces, the lateral faces, need to be regular. Then it's somewhere, yeah, thank you. Hexagonal prism, heptagonal prism, octagonal prism, like etc. That pretty much answers it. Okay, then we have the antiprisms. So what's an antiprism? I'll start with the square. Did we talk about this already?
Yeah.
Yeah. It's still, yeah. You still sort of have two squares on the top and bottom, but now they're off from each other. If you look down from above, like they're not, they haven't been just translated to a parallel plane, but they've been translated and rotated by like half of a, like a kind of like a half of like an internal angle. Yeah, basically an internal kind of central angle, and then connected with triangles, equilateral triangles in particular. So okay, antiprism. The triangular antiprism is actually just an octahedron. And then we get the pentagonal antiprism, hexagonal antiprism, heptagonal antiprism, octagonal antiprism, etc. All right, this is like a little bit boring because these go on forever. They're infinite, right? So what is an Archimedean solid? An Archimedean solid is the things we've just been talking about for the last 5 minutes. It's a polyhedron which is composed of regular polygons as faces, the traditional definition, and every vertex has to be locally the same. And the prisms and antiprism families meet this definition, but because it's like annoying that there are an infinite number of them, they're just like by agreement like not Archimedean solids. Okay, but they meet all the definitions. All right, so move all these over here. And so, as I kind of alluded to, if you take out prisms and antiprisms, you have in fact just a finite number of shapes meeting this definition. There are 13 Archimedean solids, although even that has kind of an asterisk, and we will meet them all right now. Each of them can be thought of as being formed by performing various kind of transformations on the Platonic solids. So the simplest thing you can do is truncation. And I don't know why, I mean, these are cool looking, but it's probably even easier to like see everything from the 3D shapes. We did make all these and everything, so I don't know why, whatever. This will be our first introduction, we'll talk about them more from the paper models. But if you take a tetrahedron and you truncate it, and by truncate, okay, and being a little vague about what that means, but cut off like a tiny tip in such a way that the thing you're left with has to be Archimedean, so it's got to be, of course, a equilateral triangle that you cut off. And you have to do it in such a way that the face that you leave behind is also regular. And so you really only get one choice, right? So you cut like this, and this is the truncated tetrahedron. Cool? I'll pass it around. All right, you can also truncate some other shapes. For example, the cube. This is maybe the simplest shape, right? What's a truncated cube? Well, dude, man, you just take a cube and you cut a little thing off every corner, right? And every vertex of the truncated cube is, so if you truncate a cube, every vertex of the cube becomes an equilateral triangle, and every square face of the cube becomes an octagon because you've cut. Okay, and every vertex is the intersection of an octagon, a triangle, and an octagon. Cool? Okay, so I'll just put this here. Then you have the truncated octahedron. So take an octahedron and just truncate it, man. If you cut the vertex figure of an octahedron, is a square, which is another way of saying if you cut a vertex off of an octahedron, a square will be revealed. And if you do it in a regular way, you get this kind of square. And then all of the triangular faces of the octahedron become hexagons. And so there are 8 hexagons in a truncated tetrahedron. What did I say?
Octahedron.
Blah, 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 blah. In a octahedron, there are 8 triangles. That's why there are 8 hexagons in the truncated octahedron. And there are 6 vertices in the octahedron, so there are 6 square faces. Cool. And every face is the intersection of a hexagon, and a square. All right, let's go a little faster. Okay, in addition to truncation, you can also sort of like keep truncating. All right, I really feel like we should get the. Can you get the cube octahedron? So if you take the cube, right, and you truncate a little bit, you get of course, the truncated cube. But suppose you cut a larger corner off. Yeah. Excellent. Woo. Suppose you cut a larger corner off of the cube. Well, if you cut a larger corner off of the cube, then you can still get the corners are still equilateral triangles now. They're larger equilateral triangles. But then the octagon which remains would not be regular, right? If you cut off too much. But if you keep cutting and cutting and cutting deeper and deeper, eventually the two cuts will meet, and you'll just get like a slicing off of an entire corner. And so now you've sort of truncated to the midpoint, so to speak. Truncating to the midpoint is called rectifying, and you can see this clearly from this paper model we made last summer, Project Polyhedra 1.0. This is a cube, and if you truncate so big that all the blue gets truncated, then what you're left with are squares, right? Boom. This is, we should just use these. Anyway, this is the truncated, this is the cube octahedron, it's called. It's the rectification of the cube, and it's sort of like this, I guess, is the way to think about it. This.
And also the octahedron.
Yeah, and the other thing is that the cube octahedron is kind of halfway between, because the cube and octahedron are duals of each other. If you keep truncating or something, you'll just get the octahedron back again. And you can see that by maybe actually starting with the octahedron. And if you perform rectification on the octahedron, you will also get this shape. Imagine now putting can you grab me an octahedron? If you take an octahedron, there it is. If you take the octahedron and you truncate it so severely that you're truncating to the midpoint of the triangle, and all three, then what these triangular faces become now smaller triangles, right, of 1/4 the size. The point that you truncated to becomes a square. And so can you hold this in this formation? Yeah, and so if you truncate so far, let's see, boom, then you'll have a square on the top, and this will become like these triangular faces. Cool. All right, cube octahedron. Well, all right, if you guys understand rectification, then and truncation, then we can now perform truncation and rectification on the cube octahedron. So if you truncate the cube octahedron, then what you get is a truncated cube octahedron. And the truncated cube octahedron comes from, truncate every vertex. Now, here's where it gets a little interesting because, so every vertex of a cube octahedron is the intersection of a triangle, square, triangle, square. If you truncate them, what shape do you get? Yeah, you kind of get like a rectangle actually, right? So you can't just truncate. You have to truncate and then like smush a little bit or whatever. And it's not totally obvious that such a shape exists. So, and I'm a little fuzzy on the details. But if you truncate and then smush a little bit to make it not be a rectangle but a square again, then every vertex will be a square. And if you truncate a triangle just a little bit, it will become a hexagon. And if you truncate the square, it will become an octagon. And that's what this is right here. This is the truncated cube octahedron. Also much better, in fact, to just do it with this. Yep. Woo! So what did we do? We had it like, it was like this, I guess, right? So truncate every vertex of the cube octahedron, of which there are, I don't know how many, 12 vertices in the cube octahedron? That will leave us with 12 squares. Every square becomes an octagon, and every triangle becomes a hexagon. Cool? Okay, in addition to truncating the cube octahedron, we can also rectify the cube octahedron. And the rectification of the cube octahedron is truncation to the midpoint, is the best way of thinking about it. So again, what happens now? The square on the top becomes a smaller square, truncating to the midpoint. Every vertex of the cube octahedron becomes yet another square, right? Rectangle really, but then you smush. And every triangle becomes a smaller triangle. And so the 4 triangles on the top of this cube octahedron get truncated, or get rectified into the 4 triangles up over here. This pink square on the top is the original square, 1/4 the size. 1 something the size. Sure, 1/4, yeah? Yes.
Probably.
And every vertex becomes a new square. So this is the rhombic cube octahedron. This was kind of made famous in a sketch by Leonardo da Vinci. You'll see this like some places, including my daughter has a rhombic cube octahedron onesie. As you all know from following me on Twitter. All right. Good. One more shape with octahedral and cube symmetry, and that is the snub cube. All right, now this one is like less obvious exactly how to perform this, and so the proof that this shape actually exists is probably going to be harder. I do not know it. Again, treating it as a geometric object. What is this? This is the snub cube. How do you get a snub cube? You start with the cube, man, and you take these 6 faces of the cube and you just pull them apart from each other. How much? Some. And then you take them and then you just perform like a twist. Yeah, so note that opposite square faces are not aligned with each other, but in fact been given like a kind of a twist. How much of a twist? Not exactly sure. Some. When you perform some twist, you now leave space for triangles to fit in between the squares, and you just fill it in with triangles, man. This is the snub cube. Note that this snub cube comes in 2 forms, a sort of right-handed form and a left-handed form, because having pulled the 6 cubes apart from each other, you can either turn to the right or turn to the left, and you get different shapes. They're like chiral or whatever. It's the chemistry term. They are, what do we call them? Enneomorphs or something? Enantiomes. That's the chemistry term. The geometry term is, I forget. Anyway, they're reflections of each other through like the 4th dimension. They have like opposite like chiral properties. All right. Woo! Good. Now, after this, you can repeat the entire process with the dodecahedron and icosahedron. So, if we grab can you grab me the icosahedron and dodecahedron? Because they're just much prettier. I'm like transitioning away from these shapes into that's why we made these for anyway.
Can you make any convex polyhedra based with like these and then like rectification?
Yeah, well, you just keep adding to your list of things you can do until you get them all. So it's kind of like a little thing, because they just kept adding enough transformations to make every single thing you would want. Okay, good. So here is a dodecahedron, and what can we do with it? Of course, we could truncate it. If you truncate it, then you just get the chunk. I don't know where it went. There, no, it's here.
Here.
It's the truncated. Is the truncated is also here. So if you truncate just enough so that these pentagons become decagons, and every vertex becomes a triangle. So the number of vertices in the dodecahedron, which we said is 20, means there are 20 triangles, and every vertex in the truncated dodecahedron is the intersection of a decagon, and a triangle. Cool? Say cool.
Cool.
All right, pass this on.
That is
Woo-woo. We can also, let's do this next. So if you take the icosahedron, you can truncate it. If you truncate it, what will happen? Well, what's the vertex figure for an icosahedron? It's a pentagon. So, a pentagon will be revealed, and then every triangle becomes a hexagon. So that is this. This is the truncated icosahedron. Every vertex, of which there are 12, becomes a pentagon. So 12 pentagons in a truncated icosahedron, and there were 20 faces, and triangular faces, and every one of the triangular faces in the icosahedron becomes a hexagon. So this is a soccer ball. Yeah, this is a football. Yeah, soccer balls are just truncated icosahedra with 20 hexagons and 12 pentagons. Woo! All right. Similarly, the analog of the cube octahedron, the rectification of the cube or the rectification of the octahedron, is as icosahedra and dodecahedra are duals of each other. If you truncate the dodecahedron so much that you truncate to the midpoint, well, now if you think about connecting the midpoints of each of the 5 sides of this pentagon, you would get a smaller pentagon. And then you get every vertex becomes a triangle. And this is the icosahedron. So the icosahedron is the rectification of the dodecahedron. Everyone following this? Truncation to the midpoint. It is alternatively the rectification of the icosahedron, which you can see by, just like that, right? If you truncate to the midpoint, then you get a big pentagon on the top and a bunch of little triangles. 20, I guess, because one for every triangular face. All right, good. Well, the icosahedron can itself be either truncated or rectified. If you pass these away, if you truncate it, what will happen? Well, if you truncate it, then every pentagon becomes a decagon. Every vertex becomes a square, and every triangle becomes a hexagon. And this right here, dropped several times by evil people, is the truncated icosahedron. Everyone feel it? Okay, good. Alternatively, Daniel's a bad idea. Bad idea. It's just referring to people who are careless with the shapes. Alternatively, you can rectify the icosahedron by truncating to the midpoint. So every pentagon becomes a smaller pentagon. Every vertex becomes a square, and every triangle becomes a smaller triangle. So there are 20 triangles in the icosahedron, which came from the 20 original triangles of the icosahedron. That's one way of thinking about it. Then there are thus 20 triangles in the, this is called the rhombicube octahedron. Sorry, rhombi-icosahedron.
It is rhombicose.
I don't know how to pronounce it. I just invented my own